Welcome to section 6.4, modeling data with a curve of best fit. You can find this on page 413 of your textbook. Like the other videos, I'd rather you go to the end of the textbook section before the questions and look at the in summary. And you can find that on page 418. Okay, so some key ideas that you need to understand about curve of best fit. If the points on a scatter plot, which I'll show you what a scatter plot and how to do that on the graphic calculator this lesson, seems to follow a predictable curve pattern, then it may be a quadratic or a cubic relationship. Okay, so now we have two others to pick from besides the linear, between the independent variable and dependent. So things you need to know. If the points on a scatter plot follow a quadratic or cubic trend, then graphing technology can be used to determine the graph of the equation. To solve an equation, you can graph the corresponding function of each side of the equation. The x-coordinate of the point of intersect and is the solution to the equation. Okay? Technology uses polynomial regression, so we're going to use those regressions again that are in your stat menu, to determine the curve of best fit. Polynomial regression results in an equation, which is very useful to us, of a curve that balances the points on both sides of the curve. The curve of best fit can be used to predict values that are not recorded or plotted. So that's that interpolate and extrapolate again. Predictions can be made regarding the term or the curve of best fit on a scatter plot or by using the equation. It's a lot easier to use the equation than interpreting data on the graph. Okay, so just pause the video and write down the page 418 in your learning journal, then continue on with the video. I'm going to move to page 414, which is example 1 in the textbook. So example 1, using technology to solve a quadratic problem. Audrey is interested in how speed plays a role in car accidents. She knows that there is a relationship between the speed of the car and the distance needed to stop, which is also called braking distance. She has found the following experimental data on a reputable website, and she would like to write the summary for a graduation class website. Okay, so it's a lot of data here to enter into your graphing calculator. So it says plot the data on a scatter plot. Determine the equation of the quadratic regression function that models the data. So if we go to our graphing calculator, I already punched in the data because it was a lot to punch in, but you can always pause it. So you go to Stat, you go to Edit, and it brings up your list. So I've already added the two columns. I'll pause the video and you can pause it too, to just give you a moment to type all this data in. And then I'm going to show you how to create a scatter plot using your graphing calculator. Okay, once you have all the data put in, you're going to go to second function, y equals, okay? And then you're given a bunch of stat plot options. So we're just going to choose plot 1 because we're just going to pick the first one. There's just no color on the TI-83 versus this version. Okay, so you're just going to hit enter on 1. Yours should be shut off. You're just going to move you're just going to move it to on and click enter so it's on. Okay, that's all you have to do. It should already be L1 and L2 lists, and all this you don't need to change. Next, press graph. And on your graph, you will notice that you see little dots now. Okay, so it's not in our window range, so we're going to have to change our window. So if I click on window, I'm going to look at my x values. So the lowest speed was roughly around 20, and the highest speed was roughly around 90. So I'm going to have to put that in a graph. So my minimum, we'll make it 20, and then my maximum, let's make it 95. And then I'm going to go about 5 points between so I can see all my data on the graph. Maybe that's too much. Maybe we'll go to 2 points. Okay. I'm going to go to my y value. Okay, now let us look at our y values. The lowest one is roughly, nothing's below 6, and the highest one is about 130.4. So let's make this one between 5 and 135, and we'll make each scale about 5. let's see what that does to our scatter plot when we go back into graph. Go back into graph, and you see some data points. Now, it's your job, because I'm assuming on the final exam or on questions where all of these are together and you don't know which one to choose, that you need to decide which type of linear regression this is. Okay, it does slightly curve, so you would lean towards a quadratic or cubic, but it could also look like a linear. So you'd have to try all three in this example. Okay, so first of all, since we know it's a quadratic anyways, we can do the quadratic regression to try to figure it out. So if I go back into stat and I go back to calculate, I'll look for something called quad reg. Okay, that's my quadratic regression. If I hit enter and then hit enter again, or move to calculate and hit enter, it's going to figure out my equation for me. Okay, so the calculator's thinking. So y is equal to ax squared plus bx plus c is your standard formula, and you plug your values in. So the equation for this reads y equals 0.0083x squared plus 0.5339x minus 10.45 for c. So if I take this equation and I hit y equals now, and I put it into my graph, x squared plus 0.5399x minus 10.45, and I graph this, it'll show me the line of best fit. Okay, so the line of best fit is the line that goes through the center or through most of the points. Okay, so I can do this, or I could try a linear regression to show what it would look like with a linear regression, and we could compare. So if I go to stat and I go back to calculate and say I choose 4 for a linear regression, and I go down to calculate or just hit enter, for the linear regression of this, it would be y equals 1.46x minus 31.83. If I put this into the graphing calculator, into y2, minus 31.83, and I graph it, it'll show me a different line. Okay? So this is really close to both if you look at it. But why you would choose the quadratic over the linear regression is right at the end here. Okay? This is going to keep trailing off. And it looks like my blue data points are starting to curve upward. So you would choose the cubic regression or quadratic regression. But it depends on the question, right? So it's your call how you would assume why that would be a quadratic regression over a linear regression. And hopefully it'll be a question that's more clear where this line wouldn't make sense. So for example, even if we did a cubic regression, so we go into stat, we go into calculate, and we go all the way down to cubic regression, which is choice 6, and then hit enter to figure it out, we'll get that formula, which is y equals negative 1.45x cubed plus 0.033x squared minus 0.71x plus 8.47. If I take this formula and I plug it into y equals in the third one, just to see what kind of formula I'd get. So it's not the subtraction. Remember, it's a negative 1.45x. How do you get a cubic? You go to math, and in math you go down to number 3 to get the 3 plus 0.033x squared minus 0.71x plus 8.47. So if I graph this one, I'm going to get a third line, and hopefully it's in a different color. Where's the color here? Should be a pink line. Okay, so go down to the third. Oh, it's the fourth one. Oh, shoot, I put it in the wrong thing. Okay, so let's retype it again. So negative 1.45 x to the math to the 3 plus 0.033 x squared minus 0.71 x plus 8.47. And then if I go to the bottom here, and I'll just delete this one, and then I'll graph again and see what I get from my third. Okay, so I get my blue line, which is my quadratic regression. I'll get my red line, which is my linear regression, which doesn't go through all the points in the middle. And then I don't know why my third line is not showing for a cubic regression, but it's not even showing, so therefore it couldn't be a cubic regression. Okay, so let's go back to the question, what it's asking. So plot the scatter plot, which we did, and then determine the equation for the regression. So we did that. So that's y equals 0.0083 x squared plus 0.5399x minus 10.45. So part B says use your equation to compare the stopping distance at 30 kilometers with the stopping distance at 50 kilometers to the nearest tenth of a meter. Since it's giving you the x value, the 30 kilometers per hour and the 50 kilometers per hour, we can just use our technology to solve this. So if I go back into the graphing calculator, and if I go, let's delete all the other equations that aren't part of this. So I'm just going to delete the linear one, clear, and we're going to delete the next one, which is clear. Then we're going to go back up, and then we're going to go back to our graph, and then we're going to go second function, trace, consistent graphing. Okay, so second function, trace, and we're going to choose the value 1, and we're going to figure it out at 30. So if x is equal to 30, what is y equal to? So if you're driving 30 kilometers per hour, it's saying it'll take you 13.22 meters to stop, and that'll be your braking distance. If you go to second function, trace, and you put in 50 and hit enter. So if you're traveling 50 kilometers per hour, it's going to take you 37.3 meters before you can actually stop your car. So the faster you're going, the more distance you need to brake. Okay? So let's look at the next part of this question. It says, determine the maximum speed that a car should be traveling in order to stop within 4 meters the average length of a car. So to do the opposite, or if you're given a y value into the x, you're going to have to actually use the equation. So I'm going to move over to a blank sheet and I'm going to work that out. Okay, so I take my equation of y equals 0.0083x squared plus 0.5399x minus 10.45. Then I put in my y value, which is our 4 meters. So 4 equals 0.0085 or 83x squared plus 0.5399x minus 10.45. And then I just solve using algebra to solve for x, right? So I'm going to take the 10.45 over, so it'll be 4 plus 10.45 is equal to 0.0083x squared plus 0.5399x. But if I think about this for a second, this is a quadratic function, right? So I'm going to have 2 possible answers for x. So what I want to do is I actually want to solve it, and hopefully I can factor it, or I can use the quadratic equation to get my 2 answers. So let's delete this part, or let's go back. So I want everything to one side, and I want 0 on this side. So 0 equals 0.0085 0.83x squared plus 0.5399x minus 10.45 minus 4. So I'm going to move 4 over to this side. Okay, so negative 10.45 minus 4 would just be 14.45. So 0 equals 0.0083x squared plus 0.5399x minus 14.45. So I'm going to have to put this into the quadratic equation, which you learned from last year. So the quadratic equation is x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. Okay, so this is my a value, this is my b value, and this is my c value. So when I plug this into the equation, it's going to look like x squared is equal to negative 0.5399 plus or minus the square root of 0.5399 squared minus 4 times 0.0083 times 14, negative 14.45, all divided by 2 times 0.0083. So I'm not going to show you how to type most of this into the calculator. You should know by now. So I'm going to go x equals negative 0.5399 plus or minus square root. So if I take the square root of, square of 0.5399 and I square it, I get 0.2915, and then I'm going to, a negative times a positive is still a negative, times another negative makes this a positive. So if I multiply 4 times 0.0083 times 14.45, I'm going to get 0.4797, all divided by 2 times 0.0083, and that's 0.0166. Okay, I'm going to add everything under the square root sign so I can figure it out. So 0.2915 plus 0.4794 equals 0.7709, still divided by 0.0166. Okay? So, like we did last year, there's two answers. There's a positive answer and a negative answer. So I'm going to split this up on two sides, and I'm going to go negative 0.5399 plus the square root of 0.7707 divided by 0.0166, and then I'm going to take negative 0.5399, and I'm going to subtract the square root of 0.7709, and I'm going to divide by 0.0166. Okay, so if I put the first one into my calculator, so if I put in negative 0.5399 plus the square root of 0.7709, and I hit enter, I'm going to get 0.338 divided by 0.0166. So I'm going to get 0.0166, 20.37 kilometers per hour. Or if I go to this one, it's going to be negative 0.5399 minus the square root of 0.7709, and I'm going to get a negative value. I'm going to get negative 1.42 divided by 0.0166. Now I know you're never going to have a negative kilometer per hour, so this one is not a correct answer. Okay, so your answer should be, if you need 4 meters to stop, or if you only have 4 meters to stop, you better be going 20.37 kilometers per hour so you can actually stop within the 4 meter distance you're given. Okay, let's look at example 2 found on page 416 of your textbook. The following table shows the average retail price of gasoline per liter for a selection of years in a 30-year period beginning in 1979. So in 1979, gas was 21.98 cents per liter, and 30 years later, or 29 years later, it's 115.29 cents per liter. So gas has gone up drastically, but we should all know that by now. So, use technology to graph the data on a scatter plot. What polynomial function could be used to model this data and explain? B, determine the cubic regression equation of the model of the data. Use your equation to estimate the average price of gas in 1984 and 85. And estimate the year in which the average price was 56 cents per liter. Okay, so 2 words here I want you to notice. I want you to notice the word determine, and I want you to notice the word estimate. Okay? Estimations aren't usually the determining part. Estimations are usually a guess. But in B, it's easier for us to estimate using technology. In C, we'd have to solve using the equation, but we can actually estimate using the graph, and I'll show you how. So I already graphed the data on the calculator. You don't have to see me punching in the data. You can do that yourself, so just pause the video here if you want to punch in all the data so you can follow along. So again, the data is on page 416 of your textbook. Okay? So once you're done putting in all the data, you then go back to your scatter plot. So it's second function, y equals. My scatter plot is actually still on, so I'm going to go to graph, and I'm going to notice I get an error. I probably get an error because my window. So I want to hit enter, and I want to go back into my window. So my window started at 0, and it ended at 29. So let's make it 29. Make this a 1 for my scale per each tick mark. Okay, my minimum is my Y, so that's the price per liter. So it's about 21 is my minimum. My maximum is about 116. And I'm going to keep that as a scale, maybe a 5. Okay, so when I go to graph it again, it says check size, dim a list or mismatch matrix. So I did something wrong in my list. So if I go back to stat, and I go into my edit my list, I'm just going to check to see all my list values are right. So I have 20, but I obviously did something wrong. So I'm going to go through my list and figure out what I did wrong. Okay? Okay, now that my data's right, I can actually see my graph now. So if I go back into graph, I can see my scatter plot. Now my scatter plot in this example looks a lot like a cubic regression. It's coming down, 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 down. It turns, it goes up for a bit, or no, it only has one turn, and then it goes all the way up for a bit. So what is the equation that for this cubic regression? So I go back to stat, and I go to calculate, and I choose number 6, which is cubic regression. Hit enter, go to calculate, or hit enter again if you're on the TI-83. And the calculator's thinking, and it tells me my equation. So my equation for my cubic regression is y equals 0.0123 x cubed minus 0.465 x squared plus 6.295 x plus 23.45. So if I go to y equals and I put that into the plot, I can actually see what my graph looks like and if my scatter plot makes sense. Once again, you find the cubic in the math button on 3. X squared plus 6.295 x plus 23.45. So if I go to graph this, it follows the actual pattern of my scatter plot. So this is the line of best fit. Okay, if I graph something else like a linear, it would just be straight across and it wouldn't make sense. Okay, so the line of best fit makes sense for your scatter plot. Okay, so that's part A, or pardon me. So part A, we made a scatter plot. We decided it was a cubic function. Sorry, we decided it was a cubic function. We determined the cubic regression equation that models that data. Okay, so that equation, I'll just write it on here, is y equals 0.0123 x cubed minus 0.465 x squared plus 6.295 x plus 23.45. Okay? So the second part of B says, estimate the average prices of gas from 1984 to 1985. Well, our data on our table that we punched in was years after 1979. So we don't actually know which number corresponds with 1983 and 1984. So how would we figure that out? Or pardon me, 1984 and 1985. Okay, so I'll just start numbering. So if this is 0, this is obviously 1979. This would be 1980. This would be 81, 82, 83. And then it jumps to 7. So 84 and 85 would be 5 and 6 consecutively, right? So 84 and 85. So we're going to use a graphing calculator to predict the gas prices in 1984 and in 1985. So I'm going to go back to my graphing calculator, and I'm going to go to second function trace. That way I can find my value. I type in my value of 5, not 1985. And if I hit enter, the gas price is around 44.84 cents per liter. Okay, so I'm going to write that. So 44.84 cents per liter. Okay, so what is it in 1995? I'm just going to make sure I'm using the right number, which should be a 6. So I'm going to go to second function trace again, and I'm going to hit enter for my value. I'm going to type in my 6 and hit enter. And in 1985, gas was around 47.14 cents per liter. Okay, 47.14 cents per liter. Okay, so C says estimate the year in which the average price of gas was 56 cents per liter. So I don't want to put this into the equation and solve because it'll take forever. So I'm just going to go back to my graphing calculator, and I'm going to try to move my arrow. So I got to get out of here. So if I just go back to graph, and I want to look for 56, I want to use my little cursor, and I want to move my arrows around. So when y roughly gets to 56 cents, why isn't y changing here? There we go. So I want to follow my line and see when y gets to roughly 56 cents. Okay, so roughly there's about 56 cents. We can go a little lower. A little lower down the line. And that's about roughly what we're going to get. So roughly in the 16th year after, 16th and a half, roughly 16th year after 1979 will be the answer. So roughly where's the 16th year after? Okay, so if I go 1985, then I go back to 1986, 87, 88, 10 would be 89, 11 would be 90, 12 would be 91, 13 would be 92, 14 would be 93, 15 would be 94, and 16 would be about 95. So around the year 1995 is when the gas price went to about 56 cents per liter. That's just an estimate, right? So 1995 is what we're estimating. Okay? So now, your turn. So the questions you're going to work on are on page 420, and they're number 3, 4, 7, and 9. Remember, However, you can always go back on the videos. That's why I made the videos, so you can see what I did to make sure you're answering the questions properly.